I'm just looking at that problem on the board right there. I think this is one you should all try to do right now. Find the equation of the plane through the point. -1, 1/2, comma 3 with normal vector n equal to 1, comma 4, comma 1. This is something I think we are all capable of doing, so give it a shot. Thirty seconds. All right, close enough. So here's the easy way to do this. The easy way is to remember that the components of the normal vector are the coefficients of your variables in your plane equation. So we should get something like x plus 4y plus z equal to some constant. And then we're just going to plug in the point that has to be in the plane. So we're going to plug in -1 for x, 1/2 for y, 3 for z, and we're going to get, let's see, -1 plus 2 plus 3 is, I think, 4. So we end up getting that our equation is x plus 4y plus z equal to 4. End of story. If you wanted to do it the harder way we would say, oh yeah, your vector in the plane, so vector in the plane from the point that's in the plane, negative 1/2, comma 3, to any other point in the plane, x, y, z, has to be perpendicular to the normal vector, which means that this vector here, x minus minus 1, y minus 1/2, z minus 3, dotted with the normal vector 1, comma 4, comma 1 has to equal 0. And that'll lead you to the same equation. If you dot this out, you get 1 times x plus 1 plus 4 times y minus 1/2 plus 1 times z minus 3 equal to 0. And then if you multiply this out and bring the constants to the other side, it'll be the same equation. So you can do it the easy way or you can do it the harder way. They're both pretty much the same. I will say if someone asked you to kind of like demonstrate why it works the way it does, you probably would want to do it this second way. Like if they didn't just say find the equation of the plane, but like why is this the equation of the plane? You might have to rely on making some sort of argument about like why this is what it is. Cool. Let's look at the other one in orange over there. I mean, I should ask you all, I believe the answer is no, but has anybody talked about the cross product? The answer should be no, but just in case it's not, I want to make sure. Okay, great. Cool. So the reason I asked is because there is a way to find a vector that's perpendicular to two other vectors using something called the cross product, but we don't need to know that to do it. So we want to find a unit vector that is orthogonal to or perpendicular to both 1, 1, 0 and 1, 0, negative 1. Cool. So let's call our vector ABC, XYZ, whatever you want. Let's say our vector is V1, V2, V3. I said neither of the things I said before. Okay. So here's what we know. And this is what you should, when you see the word orthogonal, you should immediately think, great. The vector I'm trying to find and the vector it's orthogonal to, the first thing you should think is their dot product has to be 0. That's the first, not that there are other things that also are true, but that's the first thing you should think of when you hear the word orthogonal. These two vectors have a dot product that's 0. So great. I know two things then. I know that I'm going to call this one U and this one W just to give them some names. You're totally allowed to do that, right? If you want to make it easier to write things down, I'm going to write U dot V just to make it more convenient. And then that's going to be that vector dotted with that vector. So it's going to be 1 times V1 plus 1 times V2 plus 0 times V3 has to equal 0. And then I also know that W dot V, which is going to be 1 times V1 plus 0 times V2 minus 1 times V3 has to equal 0. I will point out that I'm completely ignoring the fact that it has to be a unit vector at this point. What I'm going to first do is just find any old vector that's orthogonal to both of these vectors. And then after I find a vector that works, I will then find its, I'll divide by its own magnitude to make the unit vector. So great, here's what I need. I need that V1, let's do it this way. I need that V2 is equal to the negative of V1 and that V3 is equal to V1. So basically pick V1 to be a number. 1 is a very likely choice. I should say, pick V1 to be any non-zero number, right? So technically the 0 vector is orthogonal to every other vector, but it wouldn't meet the requirement because it doesn't have the right length. The 0 vector is a vector of length 0. It's kind of stupid, right? It's literally a point. The 0 vector doesn't really look like a vector, but there is a 0 vector and it is a vector that has a length of 0. And yes, it is technically orthogonal to every other vector because the dot product with it will always be 0. We're not looking for that vector. So here I would just let V1 equal 1, and then V2 is going to be negative 1, and then V3 is going to be positive 1. So a non-unit vector that is orthogonal to both of these vectors is V equal to the vector 1, negative 1, 1. And you can check that for yourself if you want. If you dot U and V together, you're clearly going to get 0. If you dot W and V together, you're also clearly going to get 0. And then we're going to take the magnitude of V. So the magnitude of V is the square root of 1 squared plus negative 1 squared plus 1 squared, which is the square root of 3. And then our final vector, well, one of our final vectors, v divided by its own magnitude, which I would call u, except I already used the name u, so I'm just going to call it, I don't know, something else. I'll just call it v divided by v, is going to be each of the components of v divided by the magnitude. So 1 over root 3, comma, negative 1 over root 3, comma, 1 over root 3. And by the words I said earlier, you might guess that there is another such vector, and there is. And there's typically when you're asked for a unit vector that does a thing, there's usually two answers. The one you find and the one that points in the opposite direction, which you just get by changing the signs of all the components. So this is one of them. I don't know, let's call it U1. And then the other one is going to be U2, which is negative 1 over root 3, positive 1 over root 3, negative 1 over root 3. Or another way to say that is if two vectors are orthogonal to each other, then any multiple of one of the vectors should still be orthogonal, right? Multiplying a vector by a scalar just changes its length. It doesn't change its direction. So if two vectors are already at 90 degrees, making this one shorter or longer or in the opposite direction shouldn't change the fact that they're still orthogonal to each other. In fact, I should say, doesn't change the fact that they're still orthogonal to each other. Cool. I like that question. Oh, yeah, that actually means that something else. So if I gave you, in fact, I want everybody to do this. Find a vector orthogonal to 5, 12. As quickly as you can. There's actually technically an infinite number of answers, but there's two really quick ones. One of the really quick ones is 12, negative 5. The other really quick one is, I'll call it W1, negative 12, 5. The process here is to interchange the two coordinates and then change the sign of one of them. Process is maybe too strong a word there. The thing you do is you change the order of the components and then change the sign of one of them. It also works if you're trying to find a vector that's orthogonal to a three-dimensional vector and one of the, well, no, actually, I'm going to say it that way. So for example, if I gave you v equal to, I don't know, 3, 4, 7, a way you can easily find an orthogonal vector would be to say, interchange two of them, change the sign of one of them, and then make the last thing 0. That would work. Or this would work. 0, 7, negative 4. Or this would work. 7, 0, negative 3. Or change the signs, right? Positive 4, negative 3, 0. Or 0, negative 7, positive 4. Or negative 7, 0, 3. I am always coming at this question with the caveat that you shouldn't be picking the 0 vector, right? That's always, if someone asks you to find the vector orthogonal to another vector, you should always think not the 0 vector, right? Not the vector of all zeros, because that's kind of just not what they want. And usually they'll say, find a unit vector, so you can't pick the 0 vector. So then if I want to make any of these a unit vector, I would just divide them by their own magnitude. Cool. So as you can see, in 2 dimensions, you don't have a lot of choices. Right? There's really only 2 vectors that are orthogonal to any given vector. And really, they're kind of the same because they're just pointing in the opposite directions. They're kind of the same. In 3 dimensions, lots of choices, right? If you have a vector, there's a whole, right? If you have a vector sticking out of your plane, there's a whole plane's worth of vectors that are orthogonal to it. And they can point in any multitude of directions. Okay, cool. All right. Let's look at that question in red. The diagonal of a cube is a line segment between opposite corners of a cube. Sure. Find the angle between a diagonal of the cube and one of the edges of the cube. All right, so let's draw a little picture here. Not my best work, maybe. Let's see, how am I going to do this? should have thought about that before I started drawing pictures. Oh well, such is life. Here's my cube. And I'm going to think of that back corner of the cube right there as being the origin. So there's my 0, 0, 0. And this is the x-axis, this is the y-axis, the z-axis, and the usual kind of setup. And I'm going to make up a length of an edge. Let's just say 1. It's a pretty typical choice. So each of these edges is length 1, 1, 1, etc. Meaning this point is the point 1, 0, 0. This point here is 1, 1, 0. This point here is 1, 0, 1. Not 1, 0, 1. Sorry, 0, 1, 0. Apologies. And this point up here is 1, 1, 1. You could label other stuff too. This is 0, 1, 1. This is 1, 0, 1. This is 0, 0, 1. So the first question asks us to find the angle between the diagonal of the cube and one of the edges of the cube. Doesn't matter which one you pick. If you're trying to find the angle between this diagonal and either this edge or that edge, they'll all be the same, which is nice. There's a lot of symmetry here. So the idea here is to write the things you want to find the angles between as vectors. So this diagonal of the cube, I'm going to think of as the vector, call it V, 1, 1, 1. And pick whichever edge you like. I'm going to pick that one there. Let's call it W. That vector is the vector 1, 0, 0. And now we have a very standardized process for finding the angle between two vectors. We know that cosine of the angle between those two vectors is going to equal the dot product of the two vectors divided by the magnitude of the vectors multiplied together. In this case, it's going to be 1 times 1 plus 1 times 0 plus 1 times 0, which is 1, over the magnitude of W, which is 1, times the magnitude of V, which is the square root of 3. So it looks like cosine theta is equal to 1 over root 3, which means that theta is equal to the inverse or arc cosine of 1 over root 3. And just for the sake of knowing approximately what the angle is, because I'm kind of curious, see here. Come on. So can you see that? I mean, it doesn't really matter if you can see it or not, but it's kind of nice to see. Yeah, you can kind of see that. Let's see. We want the inverse cosine of 1 divided by the square root of 3. And I guess I should make sure I'm in the right mode here. And I should go back a moment because that's the wrong place to put that parentheses. Cool. Yes, we're in degrees. Cool. So the angle is about 54.7 degrees. Okay, yeah. Converting this value to radians? Yeah. Right. Well, so why are we asking this question? On a quiz, not on web work? Okay. So if you're given, I mean, this angle as is just whatever the angle is. Until you write it in degrees or radians, you're just kind of expressing it as that's the angle. So I don't really have a way of saying what it's not really in radians or degrees at this point until you actually get a decimal approximation. So I could either say, like, I guess, is there more to that question there? Like, or could you say it again? I feel like I'm missing something. Right? Radians. I mean, there's no, like, I mean, really, like, until you've actually done something with this, you have to decide, like, so I should back up. Maybe the situation you were in was they gave you something special, like the inverse cosine of 1/2, or the inverse cosine of root 3 over 2, or the inverse cosine of root 2 over 2. If it was one of those numbers, then yes, you should not have given your angle in degrees. You should have given your angle in radians. Inverse cosine of 1/2 is pi over 3. Inverse cosine of root 3 over 2 is pi over 6. And inverse cosine of root 2 over 2 is pi over 4. So yes, if it's a known angle and value pair, then you have to be able to just know what the angle is and write it in either radians or degrees as specified. But here, I can't do anything until I've plugged it into a calculator and gotten the value. Yeah. No, I figured out. I was like, what? I have no idea how you, yeah, okay. That makes more sense. Cool. So then the second question there is pretty much the same idea. We want to find the angle between two vectors, but now instead of being the diagonal and one of the edges, it's the diagonal and the diagonal of one of the square faces. So I'm going to pick this square face here, the diagonal of that one. Let's call that vector u. And we're going to say, great, our vector u is the vector 1, 1, 0. The great thing about writing vectors that emanate from the origin is the point they terminate at is just what the vector is, right? This vector starts here and ends there, and it ends at the point 1, 1, 0, and the vector is the vector 1, 1, 0. How convenient. There's something else. Oh yeah, I wanted to write down what that angle was though. It was about 54.7 degrees. Neat. And then over here, same idea. We're going to find cosine of the angle between u and v. Same way. It's going to be the dot product of u and v divided by, excuse me, the magnitude of u times the magnitude of v. So the dot product now is going to be 1 plus 1 plus 0 over the magnitude of u, which is the square root of 2, and the magnitude of v, which is still the square root of 3. So, yeesh, yeah. Here I didn't rationalize that because I didn't feel like I needed to, but you could have said it was root 3 over 3. Here, for some reason, I feel oddly compelled to rationalize it. This is 2 over root 6, which is 2 root 6 over 6, which is root 6 over 3. No good reason to do that. I just felt like I should. So then our angle is going to be the arc cosine or the inverse cosine of root 6 over 3. Again, using the calculator, that's going to be approximately, let's see, inverse cosine of the square root of 6. Nope. Be careful, James. Divided by 3. I don't know about this calculator sometimes. 35-ish degrees. Neat. Yeah, I like that. Questions about that? So an interesting question for you to ask yourself might be, if you're at a point like at the center of the cube and you want to find the angle between like let's say there was a point right there and you want to find the angle between like the vector there and the vector there, you can do the same sort of thing. Kind of cool. You had a question, Claudia?
Yeah, it was just like for those on the circle.
Say it one more time. Oh, these angles here? Or these angles here?
Like read them.
So you should know the following. Here's an easy way of remembering it. Yeah, let's do this. Sure. So we have, am I making this table the right way? Yeah, sure, that's fine. We have your angle, and then you have sine of your angle, and then you have cosine of your angle. In my opinion, there are 5 angles you should know, and then the rest kind of come along for the ride. Those angles are 0 degrees / 0 radians, pi over 6 radians / 30 degrees. And I went the wrong way there, apologies. Pi over 4 radians / 45 degrees, pi over 3 radians / 60 degrees, and pi over 2 radians / 90 degrees. And the values are, there's a very kind of fun way of remembering them that makes a nice pattern. So I'm going to write something kind of stupid, but it's going to make sense. Sine of 0 is 0, but I'm going to write it as the square root of 0 divided by 4. 4? Is 4 the right number? No, I think 2. Sorry about that. 2. Apologies. Which is 0, right? The square root of 0 is 0. 0 divided by 2 is 0. But then sine of pi over 6 is the square root of 1 over 2, which is equal to 1/2. Sine of pi over 4 is the square root of 2 over 2. Sine of pi over 3 is the square root of 3 over 2. Sine of pi over 2 is the square root of 4 over 2, which is equal to 1. Look at that lovely pattern. Square root of something over 2, and something just goes 0, 1, 2, 3, 4. And then the cosine values are flipped in the opposite order. Cosine of 0 is the square root of 4 over 2, which is 1. Cosine of pi over 6 is the square root of 3 over 2. Cosine of pi over 4 is the square root of 2 over 2. Cosine of pi over 3 is the square root of 1 over 2, which is 1/2. Cosine of pi over 2 is the square root of 0 over 2, which is 0. I would say you're expected to know those at minimum. Cool. Other questions about that? I will mention I posted a handout on Leslie matrices. Has anyone been talking about that in class though? Yes. Okay. All right. Cool. Let's see. Let me look at this matrix handout real quick here. We did all that. Yeah, that's fine. So I want to point out that you all should make a real effort to get very, very comfortable multiplying matrices that are 2 by 2 or 2 by 3 or 3 by 2 by something matrices. You probably need to be good at like I don't think you need to be able to do the following to multiply. I could be wrong though. So I think this is probably a bit much. Like if you take a matrix like 1, 2, 3, 4, 0, 5, negative 4, 6, 1 times another 3 by 3 matrix, 2, 1, 0, 0, 1, 5. 607. You should be able to multiply these together without too much effort. And if it takes a lot of effort, then you should practice doing. Write yourself some matrices, multiply them out. And then you can probably find, I'm sure there's plenty of matrix calculators on the internet where you can type in a blank by blank matrix times another blank by blank matrix, and it'll spit out the result for you so you can check your work. But you want to get, you're not going to be doing a whole lot of it, but you definitely are going to be multiplying some 2 by 2 matrices together, and you want to be able to do it relatively quickly. And on this next exam, you might have larger matrices that you have to multiply together. I don't know for sure, but it's just something you should be not terrible at. So here, we multiply these together. We want to be kind of quick at it. So it's always the first row of your first matrix. Let's call this one A and this one B. So we're going to start with the first row of A, and we're going to apply it to every column of B before we move on to the next row of A. So my first entry here is going to be the first row of A dotted with the first column of B. That's going to be 1 times 2 plus 2 times 0 plus 3 times 6, or 2 plus 0 plus 18, which is 20. And then we're going to do still the first row of A now with the second column of B. 1 times 1 plus 2 times 1 plus 3 times 0 is 1 plus 2 plus 0, which is 3. And then the first row of A dotted with the third column of B. 0 plus 10 plus 21 is 31. I want to make something really super clear here that when you dot, and it is a dot product, the first row of A with the first column of B, you get the first row, first column entry of your product matrix. And when you dot the first row of A with the second column of B, you get the entry that's in the first row and second column of your matrix. And when you dot the first row of A with the third column of B, you get the entry that's in the first row and third column. It's not a coincidence, right? Whatever row and column you're picking in A and B, you're going to get that entry in your product matrix. So if someone, I will finish this in a second, but if someone asked you, like, what is the entry in the second row, third column of the product of A and B, they don't want you to multiply out the whole matrix. They want you to know that if you take specifically the dot product of the second row of A with the third column of B, you will get the thing you're looking for. So that's going to be 4 times 0 plus 0 times 5 plus 5 times 7. That would be the answer to that question specifically. It's good to be able to know how to find the thing you're looking for. And it's always just the row you use from the first one and the column you use from the second one gets you to that row and that column in the product. Kind of neat. It only took me a long number of years to really kind of make that connection. So hopefully you can all learn from my experience and learn it faster than I did. So finishing off this matrix multiplication, we get this row dotted with the first column. So 8 plus 0 plus 30. I do think pointing at the things helps me see what I'm doing, right? I'm not just like, if I didn't point, it'd be hard for me to see like it's for the next one, it's 4 times 1 plus 0 times 1. No, I think pointing 4 times 1 is 4 plus 0 plus 0. Nice. And then finally the last row with all the other columns. So that's going to be also drawing this line here is not super helpful, as you might have noticed, because I've kind of crossed out the numbers. Let me draw them again. That's going to be -8 plus 0 plus 6 is going to be -2. -4 plus 6 plus 0 is 2. That is a 1 there and a 1 there. And 0 plus 30 plus 7 is going to be 37. So take some time, spend some time, multiply matrices together just until you feel like you're pretty good at it. Sure. What else we got? We talked a little bit last time about identity matrices. I did say something kind of wrong last time that someone corrected me afterwards, but then I felt like I should say it. So I just want to point out that when you multiply any identity matrix by a matrix, you get back not the identity, but the matrix you were multiplying by. And it doesn't matter. So the identity matrix is one of those special matrices where it doesn't matter which order you multiply by something. If you have the identity matrix times A or A times the identity matrix, you will always get back the same thing. So this is a matrix that is commutative with other matrices, meaning it doesn't matter which order you write the multiplication. As long as the matrix is a square matrix. For example, if you have the 2 by 2 identity matrix multiplied by the matrix 1, 2, 3, 4, you're going to get back 1, 2, 3, 4. And that's true if you do it the other way as well. 1, 2, 3, 4 multiplied by the identity 1, 0, 0, 1 is still going to give you 1, 2, 3, 4. And again, the reason we call it, just in case you're not clear about the language here, the reason something's called an identity is because it doesn't change something else. So this matrix is called, it's called the multiplicative identity, because when you multiply by it, it leaves the thing alone. Similarly, the zero matrix, which is just a matrix full of zeros, is not talked about as much, but it is the additive identity. Just like the number 0 in real numbers is the additive identity, because when you add it to something else, it doesn't change the something else. So I'll point out that A plus the 0 matrix is still going to give you A, as long as it's the right size 0 matrix. But then the other thing I was going to say about this was that if your matrix isn't a square matrix, like if A was a 2 by 3 matrix, like 1, 2, 3, 4, 5, 6, then you have to have the right size identity matrix. So if you wanted to do I times A, it would have to be a 2 by 2 identity matrix multiplied by this 2 by 3 A matrix. But then when you did it, you would just get back A, right? Because you get 1 plus 0 and 2 plus 0 and 3 plus 0 and then 0 plus 4 and then 0 plus 5 and then 0 plus 6. But if you tried to do the multiplication in the other direction, you'd have A times I, but then the I matrix, if the multiplication is actually going to work, that identity matrix better be your 3 by 3 identity matrix. So what I'm really trying to say here is that if you have someone writing like a matrix times the identity matrix, we just assume it's the right size for the multiplication to work. And you don't really need to, but you could write that this is like I2 here because it's a 2 by 2, and this is I3 because it's a 3 by 3. All right. What else to say? Sure, this is a good one. I know I said those matrices. I don't know if I really want to get into that today. Sure, we'll do this and we'll see. So show that for any 2 by 2 matrix, A times B transpose is equal to B transpose times A transpose. Okay, so when somebody says to show something is true for any 2 by 2 matrix, you can't just pick a couple. You can't be like, oh, the matrix 1, 2, 3, 4, and the matrix 2, 4, 5, 6, and then multiply them together one way, and then right. You have to pick a generic matrix, meaning without actual numbers. So we're going to say that A is the matrix. I'm going to go, sure, I'll go that way. A, B, C, D, and B is the matrix E, F, G, H. And then we're going to do both multiplications and see that either way we do it, we end up with the same result. But we can't just pick like the matrices that are convenient to use. We have to pick generic matrices that don't have any specified numbers if they're trying to show something is true for any 2 by 2 matrix. Luckily, they just said 2 by 2, right? This statement is actually true no matter what size your matrix is, as long as it's squared. But showing it for larger matrices requires more effort. So here, we're going to do the multiplication. So first, we're going to do A times B, and we're going to get, let's see. So first row dotted with first column is going to be A times E plus B times G. First row, second column is A times F plus B times H. Second row, first column is C times E plus D times G. Make sure your letters look different. Last one is second row, second column, C times F plus D times H. And then we know that A times B transpose, you're literally just interchanging the rows and columns. So now my first row is going to be this first column. So it's going to be AE plus BG. And then that's going to be over here. It's going to be CE plus DG. And then in my second row will now be my second column. So it's going to be AF plus BH and CF plus DH. Okay, so we found AB transpose. Now let's find B transpose times A transpose. So B transpose times A transpose is going to equal, well, B transpose is going to be EGFH, and A transpose is going to be ACBD. And then we're going to multiply it out. And we're going to get E times A plus G times B, or A times E plus B times G. And then E times C plus G times D. And then F times A plus H times B. And then F times C plus H times D. And are they the same? Yes, they are. So we're good. And that's actually always true. That if you take the transpose of a product, it's the product of the transposes, but in the opposite order. Which is kind of weird, but it is true. Well, later on, we might see later on that when you calculate AB inverse, it's equal to B inverse times A inverse in the same sort of way, where you change the order of multiplication. Yeah, that feels like a good time to. So I feel like we don't have enough time to really say enough about Leslie matrices to get started on that. But let's we'll skip over that for a moment. Oh, there was that question last week that I forgot to get to. Did that question get, I don't think, let's see. I don't see the student here I think they've written it down. The one about gosh, what was the words on that one? It was like things becoming, I can't remember the words. It was some biology word where something either became a thing or unbecame a thing, and it happened like 60% of the time. I don't know. The what? It's okay if we don't get to it. I just remember that I didn't get to it last time. I said I would get to it this time, but then the student who was here who asked it didn't last time isn't here today. So gosh, I wish I remember what the word was though, because it's kind of bothering me. Anyway, let's talk about yeah, anti-gen. No, it was the one where like you had to make a 2 by 2 matrix. And it was about basically like I don't know the word. It was it was that when you, I don't know. I can't remember what it was. I'm sorry. Yeah, I know you're all looking for it right now, and I appreciate you looking because it's killing my brain. So if you find it, let me know. We'll move on though. So let's look at this. Let's find an example of a 2 by 2 matrix whose I should say, of a non-zero, meaning it's not all zeros, 2 by 2 matrix whose square is the zero matrix. So here's what we want. We want to find a matrix A, and again, we don't know what it is yet, so we're just going to make it generically A, B, C, D, but we want A squared, which is just going to be the matrix A times the matrix A. We want that to equal the zero matrix. There's kind of an easy way to do this and a hard way to do this. The easy way is just to guess. And when I say guess, I mean, so if I wanted all these things to multiply or dot, I should say, to zero, it'd probably be good if a lot of them were zero. So I might try starting by guessing something like, I don't know, 0, 0, 0, but I can't make them all zero. So let's make that last one 5. If you square that, I don't think it's going to work because you're going to get that times that. I should say dotted with, right? That dotted with that, that dotted with that, that dotted with that. But then this one dotted with that one, you have a 5 hitting a 5, and so you don't get 0 there. Boo. So try putting the 5 in a different spot. So if we try putting it like here, then it will work. Because you're going to get 0 plus 0. 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 So there's an example of a non-zero matrix whose square is the zero matrix, which is kind of like atypical when you think about regular numbers, right? There isn't a real number that's not zero, that if you square it, you get 0, right? The only number that when you square it, you get 0 is 0 itself. So matrices kind of have some degenerate properties, for lack of a better word. You get some things like multiplying to 0 in weird ways, even though neither of the things was actually 0 to start with. In fact, that's what I'm really saying here is you can multiply two non-zero things together and get 0. Unlike the real numbers, where if you multiply two numbers that aren't 0 together, you don't get 0. There was something else there I meant to say. We've talked about adding matrices and subtracting matrices and multiplying matrices, but we haven't talked about dividing matrices. And the reason for that is because we can't. There is no matrix division. There is, however, multiplication by an inverse. So I will point out. Yeah, I will point out. No, let's not do this the hard way. Doing this the hard way is terrible. So I'll point out that, oh my gosh, will I point out that if I wanted to find like 8 divided by 4, I could also think of that as the inverse of 4 times 8. So if you wanted to quote unquote divide by a matrix, which we can't actually do, you can kind of get around that by instead multiplying by the inverse. Let's look at an example. So let's say I wanted to solve. How do I want to say this the right way? Yeah, let's go ahead and go that way. I want to solve the system of equations. Let me go ahead and write something down here. Do I have a system of equations off the top? No, fine, let's make something up. So I want to solve this system here. 2x plus 3y equal to 7, and 4x minus 5y equal to 3. I would love to solve that system of equations. But instead of doing it the way you might be used to doing it, we're going to write it as an equation of matrices. So we're going to say, well, really what we have here is the matrix 2, 3, 4, -5 multiplied by the 2 by 1 matrix x, y equal to the 2 by 1 matrix 7, 3. These two things I've written, this system of equations here and this matrix equation here, are the same. They look a little different, but they represent exactly the same thing. So if I wanted to solve for x and y, I could do it the normal way, which is like take these two equations, and I suppose I could multiply this first equation by -2, you get -4x minus 6y equal to -14, and then add that to this equation. And if I add those together, I get no x's. I get negative 11y. I get negative 11 over here. That turned out nice. And I get y equal to 1. And then I can plug that back in over here and get 2 times x plus 3 equals 7. So x is going to equal 4 divided by 2. So x is going to equal 2. Cool. We could do it that way. Or we could isolate x and y by, I shouldn't even say this, but I'm saying by dividing by, not really dividing by, this matrix over here. So what we're going to do is we're going to multiply both sides by the inverse matrix. So there's a way of finding an inverse of a matrix if it exists. Here's how you do it. Of a 2 by 2. So I should say this is true for, you can find, if it exists, the inverse of a square matrix. For a 2 by 2, 3 by 3, 4 by 4, et cetera, et cetera, et cetera. It's really easy for 2 by 2s. It's kind of terrible for 3 by 3s. And it gets worse and worse the larger the matrices get. But the process for a 2 by 2 is super nice. So if A is equal to A, B, C, D, then the inverse matrix, which we write as A superscript -1, and we read it as A inverse, is equal to the following. 1 divided by A times D minus B times C, which we'll talk about later is the determinant of that 2 by 2 matrix, multiplied by, you take your 2 by 2 matrix and you interchange the diagonal elements. So A and D switch places. And the off diagonals, B and C, you change their signs. So if B was positive, it becomes negative. If C was negative, it becomes positive. But you just slap a negative in front of both of them. This matrix is the inverse of that matrix. Okay, let me ask you a question. What do you know about numbers that are inverses? What do they multiply to? 1. Always. What number doesn't have an inverse? 0. In matrices, the numbers that don't have inverses, or the matrices that don't have inverses, are the ones where the determinant is 0. Right? Because if this value here is 0, you're going to be trying to divide by 0, which is a problem. So there's a lot of matrices that don't have inverses because this quantity ends up being 0. But as long as that quantity isn't 0, these two matrices will always multiply to 1, or in our case, the identity of the appropriate size. So it should be true, and it is true, that A inverse times A should equal the 2 by 2 identity matrix. Let's do and see. So 1 over AD minus BC times D negative B negative CA times ABCD. Leave that scalar out in front. And then we multiply these two together. Let's see. We're going to get D times A minus B times C, or AD minus BC. We're going to get D times B minus B times D, which is 0. We're going to get negative C times A plus A times C, which is also 0. And negative C times B plus A times D, which is AD minus BC. And if we distribute the 1 over AD minus BC, you're going to get 1, 0, 0, 1. So it's always true that when you multiply a matrix by its inverse, if such a thing exists, the product is always the identity, right? That's how the inverse is defined. Just like in regular numbers, the inverse is defined by, oh yeah, you find the thing that if you multiply them together, you would end up getting 1. So here, what we can do now is we can find the inverse of this. If I call this matrix A, then A inverse should equal, I forgot to leave space in front here. Sorry, I'll do it at the end. So you're going to switch the diagonals. That's going to be -5 and +2 there. And then the off diagonals, you change the signs. And then you have to multiply by 1 over 2 times -5 minus 3 times 4. I usually like to leave this out in front, but I do like to simplify it. So that's a 1 over -10 minus 12, which is -22. So I would probably rewrite this as -1 over 22 times -5, -3, -4, 2. So now we can multiply both sides of this equation by that matrix. And we have to be careful here. The side you multiply on matters. So we're going to multiply both sides of this equation by this matrix on the left side of each of the things already there. So I need more room. Oh, we're almost out of time, and then I really do have to run after class because I gotta catch a plane. So last thing here, we'll take our equation here, our 2, 3, 4, -5 times xy equal to leave some space here, 7, 3. And we're going to multiply both sides of this equation by our inverse matrix. -1/22 times -5, -3, -4, 2. Same deal on the other side. Okay, here's the gist. On the left hand side here, this A inverse times A should just be the identity matrix, I2 in this case. That's going to be 1, 0, 0, 1 on the left times xy, but 1, 0, 0, 1 times xy is just going to be xy, right? 1 times x plus 0 times y, and 0 times x plus 1 times y. On the right-hand side, we're going to multiply it out. -1/22 times -5 times 7 plus -3 times 3 is -35 minus 9, which is -44. And -4 times 7 plus 2 times 3 is -28 plus 6, which is -22. And if we distribute that, we're going to exactly get 2, 1, just like we got doing it the other way. And while this might seem like a much longer way of doing it because we're just kind of learning it, it is in fact a better, faster way of doing problems like this. So there you go. Talk about inverses. Have a lovely weekend of rain. I'll be in the sun in Las Vegas. Thank you. Appreciate it. And I intend to be back. So I fly back on Monday, but I will be back in time for class. If somehow, for some reason that changes, hopefully my flight isn't delayed. But if that changes, I will certainly post on Canvas to let you know. But plan on coming to class on Monday unless you hear otherwise. What's that? Thank you. Like I don't really have any power over that, but I do think it's funny people though. Like, have safe flight. We do have class next Wednesday. Yeah, we have class next Wednesday. But if you can't make it, I understand. I won't dislike you for not making the class on Wednesday. I know it's the day before Thanksgiving. I need to hurry up and leave. Want all of this. I don't. Gotta end the Zoom. Okay, there.